And so, Sarah, your question about AEP is used for normal kidney function, but didn't see tests for kidney function after treatment. Yeah, that's when it comes to kidney function, that's one of the things that, with any types of the function of any type of disease state, a lot of these studies are inhibiting pathways. And there's usually a balance between inhibiting it 100% and inhibiting it, 90%, or trying to find that sort of called sweet spot where you're not negatively affecting kidney function or any other biological function. That you usually don't learn that type of stuff until you look for it. So if they haven't done the study looking for kidney function after, then you wouldn't be able to see that. That would probably require a completely different set of mice that are probably genetically predisposed to kidney disease. And you would then observe in that particular set of mice both, just normal versus treating them with this compound to see if there's an effect on the kidneys. Although you could look in just wild type mice and try to observe kidney function in these wild type mice, the one problem with doing that is the length of time that you're going to expose them to the compound. It might not be long enough to produce what you might see in a clinical setting when somebody's taking a drug for months or years, unless you ran this study for months or years. So you go and you find a genetic variant of a mouse that has this particular problem. There are different types of mice strains that exist for kidney disease, and you would probably just test one of those and then look for any type of problem along the way. All right, so you can see here on this slide, right, there were several different compounds that were tested, that they got data. We chose to follow up on compound 11 just because you can see that this they were specifically testing all of the different compounds, and they looked for their AEP activity, and then they looked for their activity against some of these other biological targets, right? Cathepsin S, cathepsin L, caspase 3, caspase 8. And what they're doing here is they're trying to determine, they want to make sure that they're not inhibiting these other targets, because I can't remember which of the cathepsins. One of the cathepsins leads towards heart disease. They creates heart disease. So inhibiting some of these other targets lead down that pathway. And the reason that they frequently will choose these types of targets is, and I don't know the answer to this, but more than likely the homology, right? So we're using the term, right? Homology. So the term homology, which is the percent similarity that exists between each of these proteins, is probably close enough such that if you inhibit AEP, you might inhibit one of these other four. So they're probably in the same biological class. And so what they do is obviously you look at the list of compounds here from BB1 all the way down to 64, and you can see other than the compound 64, which is maybe a few fold less potent than the rest, they're all reasonably potent against AEP. These compounds all do not inhibit cathepsin S. A few of them inhibit cathepsin L, right? So we have a few that inhibit cathepsin L. Then several of them inhibit caspase 3, and then last, a few of them inhibit caspase 8. But when we're looking through, Right, they work with compound 11, probably because they weren't as worried about caspase 3 and caspase 8 in regards to this particular study. They then, so they have AEP micromolar. Let me look at one thing. What's this difference for the IC50? Okay, Sophia. I didn't realize you had class after this. I'm going to have to, we might have to change this time to a little earlier. Make you all get up here earlier. All right. All right. So, and then in C, so we're looking at in C, so, and in B, this is against the protein. Right, so we're looking at the protein alone with the compounds. And I probably, you know, what you're looking at here is we have, right, our graph, and when we're looking at our graph, we're increasing, we have our concentration down below, and they're showing you actually, let me see what's D down here. So you have your concentration down below, and then you have your percent inhibition on the axis. And what a typical inhibition graph looks like is it goes up like this, and we get up to the top. So usually this is going to be approximately 100% up here, right? This is going to be 0% down here. And you're looking at a concentration that, the concentration values that inhibit each of these individual proteins. So I figure I should probably explain that because none of you have probably looked at it. And these numbers for AEP and part B are all going to be, you know, usually are known as, they are IC50s. So these are all going to be IC50s. And what we're talking about here, the I stands for inhibition. Concentration, right? So it's the inhibition concentration at 50%. That's what IC50 stands for. So when we're looking at IC50s, we have our, oops, move this over here. What did I do? Sorry, trying to bring my thing back into the window. There we go. All right, so the graph that I've got drawn up in the top right-hand corner, so you'd be looking for a 50% inhibition. So the point that this reaches 50%, and on the curve, and you draw the line down, and this is the concentration, right? So this is the IC50 value that we're getting off the graph. And what you see is like this curve that I've drawn here shifts left and right. And by shifting left and right, you either will increase the IC50, which means when you move to the right, if you shift to the right, the curve's to the right, you're going to increase the IC50, which means you need a higher concentration of compound, right? So a higher concentration means you have a less active compound, right? Because the more the larger this number, IC50 number is, the more compound you need to inhibit the protein. And if it shifts to the left, then you need less compound to inhibit the protein. So that's what we're talking about here in regards to these IC50 numbers that we observe. So we can see on the chart here, AEP, BB1, right? Let me just change color here for a second, right? So we have the BB1 shows at 0.13, right? This is going to be the most potent of all the compounds here. So this is the most potent compound to inhibit AEP. Whereas the compound down at the bottom, compound 64 at 2.37 is the least potent because it requires more compound in order to inhibit AEP by 50%. Does that make sense to everyone? I hope, before I go on discussing concentrations. Yes, okay, we got at least one yes. If I see any no's, then. All right, so
yes, it does.
In part C, we have the IC50s, and these are being run in a cellular assay. So in a cellular-based assay, your compound is being applied. You have your little well, right? There are cells sitting in the bottom of the well, and you add your solution of your compound into the well, and your compound not only has to float through the solution, has to enter into the cell, and then it must perform its action and inhibit the AEP in this particular case. And you can see what ends up happening is in this particular cellular assay, they see a pretty similar overall activity, right? So the numbers are different than the activity in the protein assay alone, but they have a similar, overall binding constant. Yeah, I'll get to chart D. So, and you can see, but overall, we have, reasonably potent compounds all throughout, and they're working in a cellular assay. So that's one of the things that's always important for, learning biological activity, is being able to have, especially if your target is inside of a cell, to know that your compound can actually penetrate the cellular membrane and make it in the cell and inhibit. So you can see the numbers there. And just from a biological activity perspective, these compounds here are all relatively similar in potency. Even though one's at 0.8 and one's at 0.1, there's usually a lot of error in an assay, a biological assay, at least up to twofold. So there's probably a difference between the compound at 0.11 micromolar and 0.8, but the compound that's at 0.67 and 0.4 are probably experimentally nearly identical to one another. Same thing with 0.43 and 0.29, because there's a lot of experimental error in the calculations and the pipetting and transfers of solutions and the readers. So twofold difference is probably not uncommon for not being able to say one's more potent than the other. Whereas something from 7.86 versus 0.1, you say that's definitely a different biological activity. All right, D. Steady state kinetic parameters were determined by varying the substrate at fixed concentrations of compound 11, and the Ki value was determined by global fits to the competitive inhibition equation. All right. They're measuring velocity. Let's blow this up. So we're looking at 1D. AEP page 4. All right. All right. So let me go back to that. All right. So $64. Interesting. So they don't show how they get the Ki here. They're talking specifically about the inhibitor constant. It's the one that's required to produce half maximal inhibition. It's a measure of the inhibitor's potency. And trying to get what they did in this particular art part was they were changing so they changed the substrate concentrations. So this is the substrate. So this is the material which being shown along the bottom line of the graph is they're changing the concentration of the fragment that's being cleaved, right? So that's what they're showing down below. And they're doing that, in the top line, for example, with the round dots, right? This is if they change and they don't have any inhibitor, what happens, right? Then they do the exact same thing in the next line with the squares at 0.1 molar of compound 11. The third one is they're doing the same thing with 0.25, and the last is at 0.5. All right, so this is what they're working through in the different examples. And with the when they're looking at this particular assay, they're so they went to 50%. So this is going to be 100%. I assume that they're so to get to 50. See. So 64 nanomolar concentration. I don't know how they got Ki off of this graph because this is not a typical Ki graph. There must have been some software that automatically is calculating it from this graph because the Ki is not on this graph. There must be a mathematical calculation that I'm not familiar with the way they're producing Ki. We're entering a world that's a little further away than my expertise. But I can understand the graph, which makes sense. Like as you increase the concentration of the inhibitor, you see a reduction in the turnover, right? The velocity of the reaction. You slow the reaction down. That's cleaving the substrate, and it appears to be, somewhat linear, right? As you increase concentration, you see a decrease occurs for the amount of substrate being cleaved, and from that data, they're probably plugging that into an equation for Ki. And I don't know, they don't show this reference 27. That's where they're referring to. So they refer to 27. And let's go all the way down here. Let's see if I can get there. All right. So they're referring to 27 right here. So if you were to go look up this article in Biochemistry, 1987 article, this shows you the graphical method for determining these inhibition constant Ki. And so I imagine that they're just following that method and calculating Ki from that graph. And that's what I'm not familiar with. So in order to calculate Ki, you'd need to look up that article. You want to look that up for us and bring it to us next week, Alex? Where am I? So there. It's a learning experience for all of us. So that I'm not familiar with where they're getting that information from. And what's E? We're doing an E. So in this one, they're talking about time course inactivation assays were used to generate progress curves depicting product formation as a function of time. And yes, they get pseudo first order rate constants were obtained at each concentration of compound 11. So this is basically showing that the reaction is, they were looking up the different concentrations that these are, testing the different concentrations and showing that this nearly first order reaction, suggesting that, this is a one-to-one complex, right? A first order, we all know rate constants, right? Our rate equations now, so our rate shows us that this is going to be first order with regards to the concentration, with regards to the inhibitor AEP. So this is what the information gave us here. So this allows you, when you're trying to determine the rate of the reaction, that you know that you're forming a one-to-one complex between your inhibitor and the protein. And that's what's plotted there. They basically they measure, right, the amount of product being formed in the reaction over time, right? So they're looking for the substrate that they're talking about here is being cleaved, and it's releasing a product thing that they're able to monitor, product fragment they're able to monitor, and they see over time they're a nearly linear function. And it's not going to be completely linear because as the reaction proceeds, you have a decrease in concentration that occurs, right? And that decrease in concentration that occurs is going to decrease the overall rate of apparent rate of the reaction. So this is why they call it pseudo first order. And then the last graph is F, and it says it's a replot of the pseudo first order rate constants versus the concentration of compound 11. So they took the data from here and they replot it here. And as you increase the concentration, right, when you increase the concentration, you can see that the rate constants that they calculated from the data here, and they plot that versus the data there, you can see as you increase the concentration, eventually you reach a saturation point, right? And this is the saturation point where you have your full observed rate, right? At the lower concentrations, you don't have enough compound to saturate the entire pathway. All right. Other questions? All right. Kate and Dominic, I have a question for you. Did I ever show you the chemical drawing software? Do you guys have PCs or Macs?
I have a PC.
A PC. And did I show you the chemical drawing software? Did you ever do anything? I know you use SciFinder, but
No, I don't think so.
Okay. Okay. You have a Mac, huh? You have access to an iPad or a PC? I know one of the things that, let's see, I think for homework before the next class, what might be worthwhile is that you all start to draw your particular structures. All right, so this is one of the chemical drawing softwares that's available for PC that's free for students. I will look up the link and I'll send it to you two. And for, I know, Alex, you have an iPad, so you can use the thing it's called Elemental for iPad. Sarah, well, I can't remember what your situation was. I know Sophia had an iPad too. Sarah, which do you have? Did you have a Mac or a PC? I think you had a Mac as well, didn't you? You have a PC. Oh, you use Biovia. Great. Okay. So I'll send the link. So what I'm going to ask you all to do is to start drawing your reactions out for what you're doing. So I'd like to see you all basically get ready to put together some type of PowerPoint presentation. So to draw your structures with Biovia or with Elemental. I don't have Elemental, so I can't show you that for iPads. And you can simply take, right, so let's just say over here, you can start drawing structures. So what this is going to allow you to do is, like, if we wanted to, oops, we can start drawing your structures that you're working on, right? H2, we can, right, so as you can see how it's very quick and easy to draw all of the different structures that we're working on. So you can see within a few minutes, oops, I drew that parent compound that's there. So I'd like for the reactions that you guys have run so far to date to run them. Who's at home and doesn't have their lab book? Sarah, Dominic, Gabe. So none of you have your lab notebooks. Interesting. So let me think about how I'm gonna have to figure out how to deal with this. I might need to, yeah, Alex, I know you can stop by campus. I might need to get over there. Can I mail it? I could. I might need to scan it is what I might need to do. I'm trying to think of what I can do. I might need to run by campus and pick it up so I can mail it. Something along those lines. Scan it and email. Huh. That's going to be a bit of a headache. Let me think. You could probably draw parts of your compounds from memory. Parts of them you won't be able to. Let me figure out. So I'm trying not to head over to campus. You never started with drawing anything out, you mean? Sarah, I'm not sure what you mean. You didn't start with drawing structures and the like, or with Biovia Draw.
I never started working on the stuff that you had Sophia doing.
Yes, I know. But you can draw your structures for now.
Okay.
That's fine. And I'm gonna dig up some articles for that too, that I want to send to you. I'll dig it up after this and I'll send you an article. So we'll draw, and that way you can draw on what you have. Everybody can draw the compounds that they have worked on and the different reactions they've done. So that way we all have a record of the different reactions you've run. So when you leave here, like Alex this year, so he'll have a record of the types of reactions you ran. And if somebody asks you, you have something to refer back to. That's my goal, is that when you eventually leave at the end of every semester, you have an update of what you've done for the semester, so that you have something to talk about if somebody asks you, you go on an interview or whatever. Fair enough. So I guess my homework is to try to figure out how to get over to campus. I want to do it when there's less people around, so it won't be until an evening one day this week probably. And my goal is, I'm not terrified of getting sick. My goal is not to get sick at all during the first go around. And my wife wants to stay away from disease until, because my mother-in-law lives in town and she basically wants to be able to take care of her if she needs to. So hence the reason why I'm avoiding heading to campus right now. So with that, I think what we'll do is I'll get the notebooks and see if I can scan the copies to you. And then you can, I'll send out links to Dominic and Kate for the software. So let me write this down, notebooks. Biobia draw, download. So I'll send out that information so that we can get started on this. Other questions? Because my goal is, especially the data that I just reviewed with all of you, and the article, especially the stuff that's on page 3 that we just talked about, the biological activity. I would like for you to, and similarly for the Cert 1 project, for you to have data like that in your final presentation, so you can compare and talk a little bit about, or have some background in your presentation or your slide deck about what the project is based on, why you're doing what you're doing. So that's why I wanted you guys to review this article beforehand. Other questions, comments, curiosities? Going once, going twice. Everyone surviving in their other classes. Can't see anybody's face. It's very disappointing. You can all see me. All I can see is Alex's little picture when he was a little boy. Here's Dominic. Hi, Dominic. So anybody have any other questions? Everybody else still in bedhead? See, all you have to do is get a hat like Dominic, throw it on. You can wake up, jump out of bed. I think I woke Alex up. He was probably still sleeping because he wasn't here on time. Anyway, all right. If there's no questions, then we can end right now. Alex replied. What did you reply? Oh. Maybe I just woke you up. Come on, Alex. You can own up to it. All right. So we'll talk to you guys next week. I think let's change the time to 9 o'clock. So that way Sophia can actually meet with us too. So let's do 9 o'clock instead of 9:30. New time. Same bat channel. You guys never watched the old Batman shows, did you? Same bat time, same bat channel. That's what they used to do. It was just be a television series for Batman. And that was the way they're advertising. It was from the 70s. So, all right, set your alarm. Sounds good, Alex. All right, I'll talk to you guys all later. Bye.